So I'll share my screen here. Hi everyone. This is the part 2 of session 2 of quantum computing fundamentals, organized by Emerging OTA or Emerging Open Tech Foundation. Last week we had done one session with myself and Gokhale, and today the second session we divided into 2 parts. The first part, as you heard, Professor Gokhale has covered all the essentials of vector space and metrics. And I'll move on. Before I move on, I'll just give you the last week's updates. So every week, Monday until September 27, including today, it will be evening. You will have 6:30 p.m. Pacific Standard to 8 p.m. the on live presentation. We also have recorded, the link for that is there in the meet.google.com. It is on the Google Meet. Then we also have a subscription which you can do in the YouTube, and it's available at no cost to you. Once you subscribe, you'll be able to watch the video what is recorded for session 1, session 2 onwards. Also, we have a weekly office hours listed in the meetup, in the Santa Clara Quantum Computing meetup group, and that's listed there in the what do you call the edits chat window, where you got the link, and if it is updated, we'll be updating that. With that, I will move on to the summary of session 1, session 2, what Professor Gokhale presented today, and additionally what we are going to do later. So this is a summary, and so I'll try to just summarize what was done in session 2, the qubit basic vector, the qubit state basis. That is, if you have a quantum qubit, the state basis of it and the vector basis of it are same. State and vector are almost same as far as the qubit basis is concerned, and the matrix and bracket notations. That is the part I will try to summarize of what happened. So you can see that the section 2, the session 2 of the QCF 101 includes a few things which I'll summarize, and that will be what is high dimension vector spaces, what is basis bracket operations, probabilistic measurements which we apply to quantum, and the orthogonal and orthonormal basis, what the basis is, state basis or the vector basis, what we call, the bracket notation, how it is simplifies the work, basically computational work, and then a summary of it and what will we cover in the next session. So here I go. First, recap that we had in the session 1, as well as what Gokhale covered, Professor Gokhale covered in session 2, covered qubit state or vector. State and vector are synonymous for the qubit, and the qubit itself is a spin up or spin down and represented by a 2x1 matrix, which is nothing but a column matrix. Column matrix are 0, 1, 0 in this case is spin up, 1, 0, 1 is down. So a 2x1 matrix which you see, and in front of it you got the bar with a 0 with a greater than type symbol. This is called ket. So it's a 0 ket and a 1 ket. So ket 0 and ket 1 are the two symbols representing spin up and spin down, and they are representative of the two logical states of qubits, which in themselves are 2x1. So it can be the spin up 1, 0 and spin down 0, 1. These are represented as columns, and so the probability is what is associated with this. The magnitude, like ket 0, if I say, is root 1/3 and state 1 is root 2/3. So the superposition is a linear combination of coefficients whose sum is equal to 1, which is the probability of the state. So if you take a square of root of 1/3 and root of 2/3 and add them, you will find that it's equal to 1. So the probability of the state converging to one or the other is approximately root of 1/3 and root of 2/3, and that's how you can view it as. So this is when you do square, of course, it will be 1/3, 2/3. So essentially, what we want to say is that a qubit which is representative of physical state. Qubit in itself is logical. However, it represents the physical state of a quantum system represented either as a state or vector. State and vector are synonymous, and what they represent is a either you can do representation by bracket notation, where we have pointed out ket0, ket1 here, and also columnar matrix, which is ket is associated always with a column matrix, and 0 spin up is 1 0 and spin down is 0 1. So this is the recap of what the qubit, why do we study vector, and what is the state or basis of it. This is what we will once again look at it, what the orthonormal and orthogonal basis 2 are there. A vector v, as shown here in figure this 4-1, it's on basis of x and y, two that is x cap, y cap are the two axes, and vector representation of x cap. X cap is a unity vector and y cap is a unity vector in y direction. So this, when you take a combination, that is you take a 1 unit of this plus the 1 unit of this, and vector v is represented 1 unit in the x direction, 1 unit in the y direction. That appears to be a vector v which is at 45 degree and has a 1 component x and 1 component y, as shown figure 1 left side. Now if you go to the right side, you will find that there is another vector v prime, which is not v, which is v prime, which is v prime and which is y prime. Basically, it has a component y prime, and which is y prime happens to be around, the projection of it is around, you can say root 2, and the x component is already there, which is 1, and therefore what you find that when you do a y which is root 2, that is 1.414, 1 divided by 1.414, that is even, which is obviously the vector is not in the same on the same basis as xy basis, but it is x prime x cap y prime cap basis. So those are two different bases. So the one which is on the left side has got unit 1 as the basis for x and y both, and this is said to be orthonormal. Not only they are perpendicular, but they are also unity, therefore unit of 1, and therefore they are orthonormal and orthogonal both. Whereas on the right side, they are non-orthonormal because they are not perpendicular. X cap and y prime cap, the two directions of the vector, are at 45 degree and not at 90 degree, which is what is expected if they have to be orthogonal. And not only that, it is not making sense because they are not unity, therefore they are not orthonormal. So even if you take a 1 unit of y prime cap and x cap, they still are not orthogonal, therefore they are also not they may be orthonormal, but they cannot be orthogonal. So either way, you got both. Either it should be orthonormal. The condition for orthonormal is first they should be orthogonal. If they are not orthogonal, they are not going to be orthogonal. So this is the way. So this is the summary of what we had seen. Professor Gokhale has indicated to you on the orthonormal and orthogonal and orthonormal basis, which is important from our point of view. So if you look at qubit, quantum represents a subatomic particle, and which is in some state at a given instance, right? So that is indeterminate, which we know, and that is the reason that we want to find out which state it is in. So from our information theory approach, we represent them, these physical phenomenon of a quantum subatomic particle state, as an abstraction in vector space. And vector space is all pervading in the sense that it is the mother of all, which includes real vector space, complex vector space, as well as the specific which we need for the quantum computing called Hilbert vector space. Now it can be n-dimensional. We are looking at a 3-dimension here. That is why it is H3. The calligraphic way of writing H3, that is what it is, H3, Hilbert space. You can see here. So what we have is the physical state being abstracted and represented in the Hilbert space. But how do you represent it? And one qubit, if you look at it, it is represented by Bloch sphere, which is shown to the right here. So this Bloch sphere, one qubit is in the Hilbert space, and it has got 3 axes because it's 3. That is 3-dimension. It's a 3D Hilbert space here. So what you have is one ket0, which is bar 0 greater than type symbol, that is ket0, and same way ket1. So if you take the z-axis or z-axis, you got the ket0 and ket1 pointing top and bottom. That is one of the so basis is nothing but whatever vector you got, that is the basis. So here you got a z cap, ket0 and z cap, ket1 as the 2 logical states of z, which is the which we'll use for linear combination thereof alpha ket0 plus beta ket1, that is equal to the psi or whatever you call as one of the vectors or one of the Braket representations. So you got z as the in the Bloch sphere, the z-axis is the real usage. We always use with respect to z, and center of these is nothing but a coordinate system of Hilbert space from where emanates different axes. In this case, since we are equating it with x, y, z, so you got x, y, and z. Z is top, x is to the left. You can see +1 pointing here on this side. This is another what you call space or vector space, which is x. So x plus and x minus, which is plus and minus, just +1 and -1 you can call it, or just a plus and minus. Same way you got y pointing into left side and pointing to the right out, and those are the two which are representing imaginary I minus and I plus. So you will find that because of three the same phenomena of what the qubit is can be represented as based on basis as ket0 ket1 can be represented by ket +1 ket -1, or can be ket I and ket minus I. So even though same qubit you may represent with different bases. It's like if I have a dice and I have 6 1 2 3 4 5 6, I can use the 6 bases. But if I say instead of the 1 2 3 4 5 6, if I put on the dice A B C D E F, then I'll represent as A B C D and F. So if you put a dice, what is the probability you will get one of the 6 numbers facing up? So that is 1/6 of a probability, and each one of them has 1/6, and if you add up, that will be total 1. Same way, here you got only 2 bases for one representation. So chances are they are 50-50, and you have seen in the exercise done last time. So, but if you represent in x, it could be plus minus on the same basis, but only 2 at a time. So you are getting only 2 at a time, but are they representatively same? No, they are not same. So you cannot say measure in some x direction and show that in z direction has k0 and k1, but you have to measure and then transfer and transform that. So there are transformation involved. So Bloch sphere represents a way of transforming. So any vector on the surface of the sphere is at unit, 1 unit from the center, and you can keep rotating the vector, any vector from anywhere to anywhere. Same way you can use the r theta phi. We will come to that. Psi theta, psi phi, psi z, psi x, psi y, psi z, or sigma x, sigma y, sigma z as the measurements, and that will be a separate. So let me just focus here on the representation in Bloch sphere, and you can see I have given z axis how you represent spin up, spin down as k0, k1. Same way x axis we can use plus and minus, and the spin right, left we can do in terms of with a plus I minus I y axis. And this is the standard we will adopt. In the simplest form, what can you think of this? This is nothing but the density of finding a system in a given state. And what is the system? In this case, qubit, a single qubit is the system. So the circle represents the state of a qubit, which can, if you have multiple qubits, then it's a different story. But here, all the qubits that will be present in this, if uh, we only talk of two states, one qubit is two states. So if you have two qubit, then you will have 2 to the power 2 4. If you have n qubit, accordingly, if you have 10 example 2 to the power 10, then it's a different. But for each one of the qubits, there will be one system, one Bloch sphere. So if I have two qubits, then I should have two uh, Bloch spheres representing them. And how they interact, that's a different story. But at this time, we have to understand we are focused on just one qubit on an orthonormal basis vector state. Why orthonormal? Because everything is unit vector and it is in a state which is represented by k0 or k1 only for most of the time for the purpose of quantum computation. You can change it, but then it will impact the calculation. Like if you rotate any vector in any vector from any point A to any point B can be represented by all the rotations, etc. And that is how you make the formulas and all that. Pure vector, single qubit with a unitary or unit value is always going to lie in the sphere, surface of the sphere. And that is the probability of where it is, what it is measured is proportional to the square of the amplitude of the system's wave function. And in this case, we know that we are talking of z as a starting point from where we take the angle theta. So if I have something here, then with respect to z, whatever theta I take, that is the position of that vector. And this was all formulated by a German physicist called Max Born in 1926. And even the kit notation was done by Dirac. And this is a mathematical representation, abstract representation, but actually this really translates down to submolecular particle states, and therefore this is important. Now moving on, the last again recap. So if you have two vector, now we can talk of higher dimension or higher order vector spaces. Like 3 dimension, you can have n dimension. If you do n dimension, then you start with a vector 0 to vector n minus 1, each having a coefficient a0 to an minus 1. And then vector a, if I have to represent in n dimension, it will be a0 v0 plus a1 v1 plus dot 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 up to an minus 1 en minus 1. So this we have picked up from our referred book, reference book 319, and you can see a0, a1, an minus 1 are the coefficients. And if you take two vectors and you do a dot product of the vectors vi and j, if I is equal to j, that means it is either same vector or parallel same vector, whatever, and that turns out to be that it is equal to 1. If they are not, vi and vj are in different, like x and y, they are in different direction. Obviously x is in plus direction and y is in I direction, as per the QCF, the Bloch Sphere. Then if we take those two, there are obviously what you call are, if they are not same, they are perpendicular, as well as they have what you call unit vector, unity in the vector. So if I take a Vi and Vj and if they are not equal, that means not equal doesn't mean magnitude alone, it is also perpendicular and all. So if that is the case, their dot product will be 0. But on the contrary, let me take, if I take x and x, or y and y, or z and z, or similarly Vi and Vi, their dot product will always be equal to, in this case, 1, because they are similar. Okay, they are in the same basis of their basis is same. That's the key. So if they have the same basis, which is Vi, Vi, or V1, V1, like XX, YY, ZZ, V3, V3, V4, V4, they are in the same vector, they are in the same basis, and therefore Ket0, Ket1 with the Z axis will always be equal to 1 if I equal to 2. So now let me go on to example of Ket notation. So Ket and Bra or bracket, that is the term used. So Ket is usually a column vector. So you can see if I go numerically represent a Ket A, it is a example in this case 2 minus 3i, 6 plus 4i, and 3i are the 3 dimensions, or it's a 3 dimension vector A, and it's called represented as Ket A. So in vector notation, what you represent here, that can be represented as in this case we are taking Va equal to Vb plus Vc. So we can write Ket A equal to Ket B plus Ket C. We are not represented in Vc here. We are just talking about Ket A being equal to Ket B plus Ket C. Same way, we can represent a what you call the scalar combination of a Ket vector. What we represent in vector as Va equal to MVB plus MVC, we can represent as Ket Va equal to M Ket Vb plus M Ket Vc. Or we can also say Ket A equal to, just to simplify, instead of putting Va, Vb, and all that, you can just say Ket A equal to M Ket B plus N Ket C. So Ket notation is one for representation, equivalent vector of vector representation. And you have seen one Ket A as a column matrix. So all Kets are column matrix first. And what is then the other one? The other one is Bra, which is the duality. So Ket is a column vector, whereas Bra is a row vector. And each element in the Bra vector is a complex conjugate of the Ket's element. So if we, Ket's element, Ket A is equal to 2 minus 3i, 6 plus 4i, and 3i, which is a 3 column. So you can take a complex conjugate of this. This is pointing towards this side, which is Ket side. The Bra side is this. So if you do a transpose of it, or you do a anticlockwise rotation of this, and then flip it into a row matrix of 1 by 3. So this was 3 by 1, 3 column by 1 row. Now this is becoming 1 by 3, that is 1 row by 3 column. So here Ket A is inverted to or transposed to Bra A, and Bra A equal to 2 plus 3i. So you can see the I, because it's a imaginary 2 minus 3i is a complex number. 2 plus 3i is the complex conjugate of it. 6 plus 4i similarly becomes 6 minus 4i. 3 minus I becomes 3 plus I. So you take a individual elements complex conjugate and represent as a Bra. So the Ket can be converted to a Bra. Bra can be converted to a Ket vector. So column vector and row vector are the representation. This can be multi-dimensional, but we are talking here of a single column and single row. This can be as complex as you want. It can be square matrix, it can be any of these, but at this time we'll limit to a dimension which is on a what do you call matrix representation to the bracket notation. So Va alpha equal to v beta plus v gamma. So this is bra. So not ket. So vector representation v alpha equal to v beta plus v gamma. Its bra form representation is bra v alpha equal to bra v beta plus bra v gamma, and that can be represented as bra alpha equal to bra beta plus bra gamma. Similarly, we can add the last time we did for a ket as a k and l as the coefficients to let's say scalar representation if you want. So v alpha is equal to k v beta l v gamma, and the same thing can be represented as vector wise bra v alpha equal to k times bra v beta plus l times bra v gamma. This can be also represented in simple terms as bra alpha equal to k times bra beta plus l times bra gamma. So this is bra portion of it. So we saw the ket portion of it, we saw the bra portion of it. Mathematically, we see how the complex numbers are getting manipulated. So there are some notation called star and dagger, which are commonly used. For Hermitian, we use the dagger as the symbol, which is like a dagger you carry in hand. And for normally complex, we use star as the complex conjugate. So transpose of complex conjugate of a particular vector with a dagger symbol is what you do. So if you have a dagger, b dagger, then you have to separate a dagger and b dagger and sum, and individually you have to go into a what is component of it and take a complex conjugate and transpose accordingly. You have to calculate. Now let's go to the third one, which is very important, most important. I put it. No, yeah, this is not. This is just a representation of V1 cat and V2 V1 bra. The reason why we have got this is to ensure that we can show what you can do with a column vector and to a row vector transpose, and then show that how a V1 cat can be converted to V1 bra by using the transpose of A B to A star B star, which is nothing but complex conjugate after doing the transpose. The same thing, and this is another example. But most important for us in our quantum is bracket. So bracket notation is your bra and ket, they are back to back, they are shown, and there is only a single arrow, not two arrows which normally would expect. If you are taking a bra of V1 and a cat of V2 here, you are seeing two, but these two are merged and put as a single. This is called as bracket. This is the inner product of two vectors. So if you have two vectors, V1 with a AB, column AB as a representation of it, and V2 as CD, and if you take a dot product, then you will calculate A star. We are taking the transpose and complex conjugate of it. Transpose means you are going to say flip the anti-clockwise A and B, and then take a whatever, if it's A and B are complex, then you take the complex conjugate of that and multiply by CD. And then if you do a simple multiplication, we already looked at, Professor Gokhale presented to you, AC A into C plus B into D is what is the result. Now, so dot product is a product of bra covector Q, in this case bra Q, by a ket column vector which is ket K. So it is called as bracket and denoted by Q, bra Q, ket K. So QK. So for a just what you would expect from this linear algebra is Q, bra Q, QK bracket. You can just put it as bracket. QK bracket means Q bar K bracket. So QK bracket is equal to Q1 star, Q2 star. So Q has a component Q1, Q2, K has a component K1, K2, like we had in the vector ABCD. And then we can say Q1 star, Q2 star, that is the complex conjugate of the Q, and then multiplied by the ket. Bra means row, and so K1, K2, which is the column So if you take combination of this is nothing but summation of q j k j. J runs from whatever to whatever, 1 to 2 in this case. It can be any, as many you want in the what do you call n dimensions. So we have shown here a similar thing, but here obviously we say that v1 v2 kit bracket v1 2 is equal to 0 if v1 is not equal to v2, and if v1 is equal it is 1. So this is very important because dot inner product or the dot product are same is what we use for most of the computation to simplify the computation for the and note the product is scalar. So the output of this is a 0 or a 1. Example, x cat y cat 1 0 0 1. These are our nothing but 1 0 was our what you call ups, and in the z direction basis cat 0 cat 1. So that was the spin up, and 0 known as so that's how we take, and you get out of this is coming 0, that means x and y are orthonormal. That is what it means. If you get a 0 in this case, that means they are orthonormal, and if they are not, sorry, they are, if v1 equal to v2, then it is 1, that means they definitely same or similar or parallel. Okay, so this is what we have got here, and we move on to next one. Bond's rule. Yeah, this is the same thing, but because we have alpha kit plus alpha. In this case, what happened? Up arrow and down arrow are representation of the abstract representation of kit 0 and kit 1, and this is alpha beta belong to C2 complex. So we are taking kit psi as the alpha of up arrow, that is up arrow kit, and beta down arrow, which is nothing but kit 0 kit 1, and the probability like flip of a coin head tail. Similarly, dice 1 2 3 4 5 6. So we are taking probability based on the up arrow down arrow being kit 0 kit 1, and so it is one or the other. It will, if you try to measure, it is anywhere. So if you have a coin you flip, and suppose it either falls to head nor falls to tail, it is in between, and until it falls on one side you don't know what it is, and that is the condition usually. That's the quantum. It is in n number of states, you don't know which stable state it is going to fall. In this case there are only 2 states, so logical 2 states, it will fall into 0 or 1, and accordingly we will measure that, and the probability it will be what, that depends on how you provide the initial inputs, and therefore all measurements are always depending on how you input, because these are reversible. Remember, when we talk about a quantum circuit or a gate, they are reversible. If they are reversible, so if you know the output and if you initialize the input, then only you will know the output. If you don't initialize, then you don't know. And even when they initialize, you don't know whether it is in the state 0, logical state 0 or 1, and the probability is there. This is a probabilistic computation, and therefore this is the way. But you do have to measure at some point of time. How you measure, because it is non-cloning, as you can't clone it, so you will lose. So that is why the importance of a dot product. If you have multiple qubits in the same state, and parallelly there are 10 of them representing the same thing, and 9 may fail, 1 may not fail, so still you can conclude based on that. So that's the presumption here, and that will go as we go to the higher classes, we'll see that. But dot product of the same to same is nothing but 1. So if you take a self dot product of itself, it will be 1. And but if it is not, it is like x and y which are different, then you got a 0 already, we saw that. In summary, vectors and metrics are two major forms of representing quantum wave and particle duality in nature. We also have kit and a bra and a bracket notation to support that using the vectors or metrics or bracket notation for simplicity. So this is all integrated by use of Dirac Braket notation, as we said. And bracket notation defines the quantum states of K0 and K1, and together with superposition state of the qubit. The state or vector basis are abstract notation and can be derived for 2D, 3D Cartesian as well as Euclidean space, which we understand. But the one Hilbert space, which is hyperspace, like a hypervisor in the case of a virtualization, similar thing. This is a hyperspace, but it is in the Hilbert's H3 or Hn, an ending space, n dimension space. So this session, what it showed is how you can use dot and along with dot products or inner product along with matrix operation to unify vector space as a superset of Hilbert space used for n dimension hyperspace. The vector evaluation we list are key to mathematically way to operate in a real and abstract domains to understand quantum. Of course, you can understand the quantum computing if you understand the abstract domains, which is what, because otherwise 2-3 dimension Euclidean everybody understands, but these are not, these are in the, every quantum operation is a operation of what you call um, uh, it's so that it's a vector operation, at the same time it's a tensor operation. So all operations are tensor operations, and because it goes into n dimension. And Bloch Sphere is a visual means to simplify the concept using z-axis projection or z-axis projection of any vector or metric representation and bracket notation. So this is all we have. We have laid the foundation. We hope that you will be able to go to additional reading necessary, even elementary 12th. Uh, those who are participating from India, you can use the English also instead of English. Others can look at the English references. And Bloch Sphere, there is a here. When I say B is basic, and this is one of the mandatory ones, Bloch Sphere must watch. The rest of them, it's up to you if you have time. Also, you can read the UC Davis way of representation in the public domain, what they have, and mathematically you can look at the bracket. So this is all we have for this week. Now, what are we going to do? Is we have problems, the session, and Professor Gokhale had presented to you several of them. You might be able to use the collab as well as if you want, you can use other tools. It's not necessary that it has to be collab. Um, you can use a notebook. Uh, so it depends on what is your choice, and you can do it at your local machine also, as long as you have a Python interpreter, maybe Visual Code or Jupyter Notebook or whatever you have, you can use and try solve this. I just said, and you remember we have a what you call office hours on Wednesdays nights. So maybe those who can participate. I kept it in the night because we have people from India as well as US, so we want both of them to participate and gain out of it. Hopefully, the best time we could offer we have done. And finally, what are we going to cover next week? We are going to go into our Dr. Wong's book on Introduction to Quantum Computing, which is used by San Jose State University, and proceed to the next session. Of course, we are not going by chapter. We have our own sessions defined, but we are referring to wherever we are using. Like example, 3.0 refers to a quantum mechanical state superposition measurement, which is 5.2 of which chapter there. Same way, we are also covering basis and uncertainty principle, which is wave and particle equation, including the and the photon representation, which is more on the what you call particle representation. So you have photon as a particle as a wave representation of the uncertainty, the position to the motion. So you all understand the relativity theory. You cannot have certainly some point because the motion goes along with the energy level change, and states are referred by the energy at the end of the, call it entropy or whatever. So how the states change, we'll see using uncertainty. And we have bracket operation. Bracket we have seen notation as such. We also will do some operation by using dot product, maybe cross product. I don't know whether we are using cross product. Mostly it will be dot product and 1 or S0 to resolve a lot of things. But since they are in the different uh, bases, so the transformation has to occur from different spaces for quantum. And we are talking 1 qubit right now. When we go into qubits which are 2, then we'll have to use the local communication or uh, it could be a long distance communication, whatever it turns out to be for entanglement and teleportation. So we'll come to those. But before that, we go to that, we have to really understand what is the eigenvalue of a vector and what is eigenvectors and what are the values associated and diagonal metrics and all that. And then same eigenvalue, eigenvectors, uh, we it's mostly magnitude, but we have to look at the phase factor. How do we have a unity, but we are in different directions. So if you take a in Bloch sphere one vector and then you keep rotating, then it has a different phases. So how do we change the transform the phase, which we'll have to look into. Magnitude is well taken by the eigenvectors or metrics, but phase is not. So how will they adjust the phase? And some of the problems will be next one. So with that, I'll close my presentation for the day. Hope to see you again in the next session. Thank you very much.